Hey guys, how are you all? I hope everyone is doing fine. So, after a very long time, I'm back with a new series of videos of DS problem solvings. Right, so the problem today we are going to solve is check for BST on Geek4Geeks. So, here it is asking us to check if the given tree is a binary search tree or not. So, let me tell you a brief about binary search tree. So binary search tree is nothing but a tree on which you can apply binary search, right? And as you know that the logic for binary search is that we jump in the mid, right? So everything below the mid should be less than the mid, and everything above the mid should be higher than the mid, right? So if any tree follows the same, like here as you can see in this example, it's 2, and the left from the mid, right, the left from the root, right, is 1, so 1 is less than 2. So okay, this is valid. And if we will check the right subtree, then 3 is greater than 2, right, then it is also a valid case, right? So in tree we talk in terms of left subtree and right subtree, right, and leaf nodes and nodes. So don't be confused. Any node which is last in its hierarchy is the leaf node, and anything which is left from the node is a left subtree for that node and that root node, and anything which is right, then that is a right subtree from that root node. Same, right? Here as you can see in this example, there is no left tree. For 2, this complete is right subtree. For 7, this complete is 6 subtree, right? For 5, this complete is right subtree, right? And 6 is the leaf node, right? Okay. So here it doesn't follows the rule. As you can see, 2 is greater than 7. It's fine. It is a valid scenario. But 6 is less than 7, which is not a valid scenario. 6 should here anything which is here needs to be greater than the root, right? Because it is at its right? So here it could be 7, it could be 8 and bigger than 8, right? Also binary search tree do not contains sorry for the interference, so many calls. Okay, so yep, this is an invalid BST because 6 is smaller than 7, and it needs to be bigger than 7 to be a valid scenario. Same here for 5, right, and same for 2. 2 needs to be greater than 9, and 5 needs to be greater than 6. Anything which is anything which is at right of any node needs to be higher, right? So 5 is at right side of 6, so it needs to be higher than 6, right? Okay, so we are going to solve this problem using recursion, right? By using recursion, it will be a pretty quick and very simple problem, right? So let's see how we can do this. Okay, so I am going to create a helper function for this, right? So let's return check BST, and this check BST is going to be our helper function. It will take 3 inputs, right? First will be definitely root, second would be integer dot min value, and third needs to be integer dot max value, right? Okay, let's create function check BST. The return type is going to be boolean. It will return true or false, whether it is a valid scenario or not. The first input is going to be root of type node, second is going to be int min, third is going to be int max, right? These are the arguments for the function. And then at first we will check the input which is coming to this function, whether it is null or not, right? So if it is null, so a null tree is also a BST, right? So as you all know, null tree is a BST. So let's check for null. Okay, if root equal to null, right, simply return true. Okay, if it is null, then it's true, right? Else we will start our recursion. Root dot data should be greater than min, and root dot data should be smaller than max, obviously. Then we will call our check BST function. Okay, we will first pass root dot left. We will first check for left. For left we are going to give min value, right, and max value could be root dot data, right? So it should be less than root dot data, right? So max could be root dot data, because we are checking for less than, right, here, not less than equal to. Okay, and then we will check for right subtree. We will give root dot right, then we will give root, and then we will give root dot data, because min could be root dot data, right, because it's a right subtree, and max could be anything which is coming from the top, right? First it will be integer dot max value or min value, and then it will break down, right, in recursion. So recursion will take care of that, don't worry. Okay, let's give it a quick run, and then I think you will be able to understand, right? Okay, so it's passed. Our expected output is same as our output is same as expected output. So okay, let's see using this example. Okay, here, so first we will call check BST, right? We will give the root, which is 2, right? And sorry for interference. Okay, so we will pass check BST. The arguments will be such as 2 will be the root, integer dot min value will be the min, and integer dot max value will be the max, right? It will come here, it will check whether root is null or not. In this case root is not null, because 2 is the root, right? So it's not null, so it will not fall in this condition. It will come here, it will check whether root dot data is 2 is greater than min, right? Min is minimum value of integer, right, minus something, I don't 32,000 and that value, right? So then it will check for root dot data is less than max. Yeah, this condition is also satisfied, as all these conditions are AND conditions, right? So it will check for all. Then we will call check BST in recursion, right? Here this function will get called. Okay, so this function will get called with value root dot left is equal to 1, right? 1 will come here. Min is the integer dot min value, and root dot data is 2, right? Okay, this function will get called, it will come back here again. Now it will check whether root is null or not, right? Root is not null, root is 1, so it's not null, it will not fall in this condition, it will come back here. Okay, root dot data is greater than min, yes, 1 is greater than min. Okay, root dot data is less than max, yes, 1 is less than 2, max is root dot data is 2, right? Okay, it will again come here, and it will again call itself, right, with value root dot left is null, right? So it will pass null to this function. Okay, min would stay integer dot min value, and max would be 1 this time, right? It will come back here. Here we will check, okay, root is null, okay, it is null, it will come back, root is null, so we will return true. Okay, now it will come back here, the second last call here. Okay, for 2, the call for 2, so 1 returns true, right? There is no right subtree, then it will not fall here, so it will come back here true. Okay, same will happen for basically to right also, right? It will pass root dot right, here, and it will fall null and true. Okay, then true, it will be, everything will be true, and 2 will get true for this call, right? Okay, now it will come back here, and it will check for right subtree, right? So root dot right will be 3 here, root dot data will be 2, max would be max. Okay, max value, integer dot max value. Okay, it will come back here, again it will check, okay, it is not null, 3 is not null, it will come back here, and it will again pass its left, there is no left, it will return true, then it will again pass right, then there is no right, it will return true, and then 3 will also return true to 2. Okay, 2 will return 3, and then this whole function, whole recursion will stop, and everything will return true. True will come here, and this function will return true at the final output, right? So this is how the flow will go in the given problem. Let's run for all the test cases, submit the code. It will check for almost 120 test cases, and everything has been passed. Congratulations, we just learned how to check for a binary search tree. Okay guys, see ya, bye bye, see you soon. And also don't forget to like, subscribe.